Hello everyone, my name is Joomi and I'm pleased to present our study on the novelty effect on learning outcomes in virtual reality. This research was conducted in collaboration with my wonderful colleagues, Chen and Basu. Virtual and extended realities are gaining increasing attention as educational tools, leveraging their immersive capabilities to help learners engage with educational content. However, although many studies have found that VR-based learning promotes enjoyment and interest, there are mixed findings regarding its actual impact on learning outcomes. Some research suggests that while VR can enhance engagement, it may not always translate into improved knowledge retention or comprehension. Research also indicates that novelty effect, or a heightened sense of engagement when encountering new technology, can influence learning. The key question we had was, how does the novelty effect influence cognitive processing and behavioral engagement in VR-based learning over time? Imagine a student who has never used VR just entered a new virtual environment. They may feel curious, excited, and eager to explore, walking around and trying different functions. Conversely, they may also feel nervous or uncertain about what they can do, which may limit their interaction with learning material. Understanding this variability in learners' initial experiences highlight the importance of studying how novelty affects their ability to focus on educational content and process information over time. Previous research suggests that while VR can facilitate engagement, it can also distract from primary learning content. However, most studies focus on short-term effects. Our study extends the research by incorporating the limited capacity model of mediated message processing, or LC4MP, to examine how learners allocate cognitive resources in virtual reality over time. According to LC4MP, the cognitive system has limited resources that must be distributed between various environmental information and tasks at a given moment. Specifically by allocating resources to encoding, storage, and retrieval of information. Encoding refers to capturing new information and transferring it to working memory. This model suggests that novel elements in VR triggers an orienting response, which initially enhances encoding by directing attentional resources to the stimulus, but too much novelty may overwhelm cognitive capacity, hindering encoding efficiency. And storage involves consolidating it into long-term memory, and retrieval is the process of accessing stored knowledge when needed. Novel elements in VR may initially draw attention but could interfere with encoding. By examining this process longitudinally, we aim to provide a more comprehensive and theory-guided understanding of virtual reality's impact on learning outcomes. In this study, we considered two key processes of learning in immersive virtual environment. Information processing involves encoding new information into memory, followed by a storage and retrieval, which depend on subsequent cognitive resource allocation to encoded information. Exploratory behavior refers to actions like locomotion and object interactions, which may either support or interfere with learning. And these behaviors may influence learners' cognitive load as well. Taken together, our study aimed to ask these questions. How does the novelty effect evolve over time? And how does it impact information encoding and storage? And how do exploratory behaviors in VR impact learning outcomes? We hypothesized that initial novelty would restrict encoding but improve over time. Exploratory behaviors would decrease as users acclimate to VR, and learning outcomes would improve as cognitive resources are reallocated. So in our three-wave longitudinal study, 25 participants engaged in a virtual reality-based learning experience over 3 sessions, approximately 1 week apart. In each session, they watched a biology lecture in a custom-built virtual environment. Our virtual environment was designed to simulate a bright and cozy living room space. There was a couch, coffee table, and a large screen where participants watched lecture videos. Participants could use their remote controller to start the lecture. Additional interactive features included a kitchen area with objects that could be picked up, although these objects are not tied to learning materials. This design allowed us to observe how learners divided their attention between the lecture and exploratory element. We measured recognition memory to examine cognitive allocation to encoding using a signal detection test in which participants read statements and had to decide whether they were part of the lecture content. A correct identification or hit indicated successful encoding, whereas the false alarm suggested misattribution. Cued recall was assessed using fill-in-the-blank questions where participants had to recall key terms from the lecture. And prior virtual reality experiences and biology knowledge was accounted for as control variables. Exploratory behavior was measured through instances of teleportation and object interactions. While participants could both naturally work and use teleportation, given the limited physical space, they were encouraged to use teleportation when moving farther distance. And object interactions included picking up virtual objects, which were not directly related to the lecture content. These interactions served as both novel stimuli and potential distractors from learning. And through these behaviors, we wanted to understand whether engagement with virtual environments supported or hindered learning. Now, let's talk about the result. So recognition memory significantly improved over time, showing that as novelty diminished, learners allocated more cognitive resources to processing educational content. However, cued recall remained stable, suggesting that encoding improved, but storage processes did not show significant changes. Exploratory behaviors, including teleportation and object interactions, showed a decreasing trend but were not statistically significant. We also found an interesting interaction effect. Participants with high exploratory behaviors demonstrated a more immediate improvement in recognition from time 1 to time 2, while those with lower exploratory behaviors showed delayed improvement, only increasing significantly between time 2 and time 3. This implies that engaged exploration may facilitate learning rather than hinder it. So our findings suggest that exploratory behavior in VR may not always be a distraction as novelty diminishes. Instead, engaged exploration may facilitate cognitive resource allocation to overall virtual experiences, even when interactive elements were not directly related to the lesson. Although this warrants future research, participants who engaged more deeply with the virtual environment seem to sustain cognitive engagement, potentially driven by approach motivation and heightened attentional focus. We hope our study contributes to the understanding of how novelty and engagement interact in virtual reality-based learning over time. The VR's novelty initially impacts encoding, but it diminishes over time, allowing for improved cognitive engagement under certain conditions. Future research should explore these conditions to optimize VR learning. There are also limitations of our study. Using only biology lectures may limit generalizability, as novelty effects might differ across individuals. A control condition with less immersive media could further isolate virtual reality-specific effects. Additionally, the trends observed across specific time points may reflect variations in lecture difficulty on topic complexity rather than solely the novelty effect. Additionally, future studies should examine how different exploratory behaviors impact retention beyond initial encoding. Finally, we would like to thank our research assistant who helped with data collection. Thank you for listening.